Hello everyone, this is Mr. Brian or Lasan Cordova, and our topic for today is logic. Logic is the basis of all mathematical reasoning and of all automated reasoning, generally labeled as science of reasoning. The importance of mathematical logic is that the rules of logic gives precise meaning to mathematical sentences. These rules are used to distinguish between valid and invalid mathematical arguments. These rules help us understand and reason with statements such as this, which in simple English means there exists an integer that is not the sum of two squares. In order for a reason to be valid, a set of rules must be followed, and it also provides forms and norms for the validity and acceptability of arguments. The study of logic helps an individual to increase his or her proficiency in reasoning and make a good judgment. What is a proposition? A declarative sentence or a statement which is either true or false but not both is called a proposition. It is the basic building block of logic. From the word itself, proposition means you propose a fact, whether it's true or false. In English language, we have four types of sentences. Number one is the declarative sentence or statement. Then we have the mere sentences, questions or interrogative sentences, which ends in a question mark. Commands or imperative sentences that ends in a period like a declarative sentence but tells a command. Exclamation or exclamatory sentences, which ends in an exclamation mark. Here are some examples of proposition. Number one, puppies are cuter than kittens. Number two, I am a married man. Number three, 8 is an even number. 4, x minus 2 is greater than or equal to y. Number 5, this is the last entry on this list. Propositional logic is a mathematical system of reasoning about propositions and how they are related to one another. Propositional logic enables us to formally encode how the truth of various propositions influences the truth of other propositions. It determines if certain combinations of propositions are always, sometimes, or never true. Determines whether certain combinations of propositions logically entail other combinations. Variables and connectives. Propositional logic is a formal mathematical system whose syntax is rigidly specified. Every statement in propositional logic consists of propositional variables combined via logical connectives. Each variable represents some propositions. For example, you wanted it, or you should have put a ring on it. Connectives encodes how propositions are related. For example, if you wanted it, then you should have put a ring on it. Each proposition will be represented by a propositional variable. They are usually represented as lowercase letters. For example, the most common are P, Q, R, S, and more. If we need more, we can use subscripts, P sub 1, P sub 2, and etc. Each variable can take one of two values only, true or false. For logical connectives, we have the first one is negation. This reads not P. The negation of P is true if and only if P is false, and vice versa. The negation of P is false if and only if P is true. Next is conjunction. This reads P and Q. The conjunction of P and Q is true if both P and Q are true. Next is disjunction. This reads P or Q. The disjunction P or Q is true if at least one of P or Q are true, meaning you have the choice, so you can always choose true. Next is implication or conditional. This reads P implies Q. Implication means if P is true, then Q is true as well. But it says nothing about causality. It just says that if P is true, Q will be true as well. So we are going to focus on the implication or the Q statement. Double implication or biconditional. This reads P if and only if Q. Intuitively, either both P and Q are true or neither of them are. Think of it as an equality. Two propositions must have equal truth values. Examples. The negation of we have class today is we do not have class today. The conjunction of today is Monday and we have class today is today is Monday and we have class today. The disjunction of today is Monday and we have class today is today is Monday or we have class today. For the implication, if today is Monday, then we have class today. For biconditional, today is Monday if and only if we have class today. Truth tables. A single or simple proposition will have a truth table consisting of two rows because its truth value is either true or false. For example, the negation of P, we have either true or false. Negation of this are false and true. For compound proposition consisting of two simple propositions, there will be four rows, and we use the connectives. We have the compound propositions P and Q, P or Q, P implies Q, P if and only if Q. We will have the combination of two truth values for two simple propositions. Okay, so we have true, true, false, false. Then for Q, we have true, false, true, false. So we put it alternatively so that we can have the combination if both of them are true, if P is true and Q is false, if P is false and Q is true, or both of them are false. For P and Q, it is only true if both of them are true. And if they are not both true, they are false. For P or Q, they can only be true if both of them are true or one of them is true. For implication, this can only be true if they are both true, the implication is true, or false implies false. For biconditional, we have if they are both true or both are false. Okay. Tautologies. When all substitution instances of an argument are all true. For example, a truth table for P implies Q or Q implies P. So this is a combination of propositions. So we have the truth table. So we first get the truth values for the inner arguments. P implies Q. Again, we focus on the implication if they are not the same. Truth implies truth, that is true. Truth implies false is false. False implies true is true. Both false, that is true. Q implies P, meaning true and true, that is true. False, then true, that is true. True and false, that is false. And false to false, that is true. Now for the combination using or, true or true, they are both true, that is true. False or true, there is one true, so you can choose true. True or false, you can choose true. And both of them are true, we have truth. As we can see, they are all true. That means all substitution instances of this argument are all true. This is a tautology. For the contradiction, when all substitution instances of an argument are false. For example, the truth table for P if and only if Q and P if and only if not Q. Okay, so we have the truth values for the propositions P and Q. Now here, another technique is we put the truth values directly under the connective. So number one, we focus on the P if and only if Q. So true if and only if true, that is true. True if and only if false, false. False if and only if true, that is false. False if and only if false, that is true. Next, we copy the truth values of P. True, true, false, false. Then get the negation of Q. So true becomes false, false becomes true, true becomes false, and false becomes true. Now we can get the biconditional between P if and only if not Q. True, false, that is false since they are not equal truth values. True and true, that is true. False, false, true. False and true, not equal, so false. Now we finish off with the connective end. We focus on the number 1 and number 4 columns. True and false, that is false. False and true, that is false also. False and true, false again. True and false, false again. Since and can only be true if both of them are true. So as we can see, the final truth values are all false. For the contingency, when it is neither a tautology nor contradiction. So example, for the truth table of not P implies not Q, if and only if P implies Q. Again, we put the truth values under the connectives. So number 1, the negation of P. So we have false, false, true, true. Then the negation of Q, false, true, false, true. Then for their implication, false implies false, that is true. False implies true. So we focus on the implication true. True implies false, that is false. Truth implies true, that is true. Next, we focus on P implies Q. So we have truth implies true, that is true. True implies false, that is false. False implies true, that is true. False implies false, that is true also. Then lastly, get the biconditional. So we focus on the third and fourth columns. So true, true, they're the same. So we have true. True and false, they're not the same. False. False and true, that is false also. Truth and truth, they are the same. So we have truth. Then we can see that it is neither a tautology nor contradiction. So this is a contingency. For multiple propositions, we add another column for one more proposition. Then we put the truth values of these columns like this. So the first half for P are all true. Then the second half are all false. For Q, we alternate every other row. So true, true, false, false, true, true, false, false. And for the third, we have alternating values. True, false, true, false, true, false, true, false. Then for the arguments, we can only focus on the connectives between two propositions at a time. Now let's focus on the conditional statements P implies Q. Conditional statements are written in the form P implies Q, if P then Q, if P, Q, Q if P. P is called the antecedent or the action. P is called the consequent or the result of the action. For example, if you do not pass your requirement on time, that is the antecedent. I will give you a failing mark. That is the consequent. As you can see, for every action, there is a consequence. The converse is if the premise, or it is the antecedent, and the conclusion, that is the consequent, of the conditional statement is interchanged. That means we interchange the position of the P and Q. So Q implies P. The inverse is if the premise and conclusion of the conditional statement is negated. So from P implies Q, we have not P implies not Q. So that is if not P, then not Q. Then we have contrapositive, that is if the converse, so converse Q implies P, is negated. So not Q implies not P. If not Q, then not P. So examples of this conditional statement P implies Q. If two lines intersect to form a right angle, then the lines are perpendicular. The converse of this is if the lines are perpendicular, then the lines intersect to form a right angle. While the inverse, if two lines do not intersect to form a right angle, then the lines are not perpendicular. Contrapositive, if the lines are not perpendicular, then the lines do not intersect to form a right angle. For the logical equivalence, two propositions materially equivalent if they always have the same truth values. If their biconditional statement is a tautology. So for example, the negation of P or Q is a logical equivalence of not P and not Q. To verify that, we have the truth values for P and Q. Now let's focus on the truth values for P or Q. So this becomes true if one of P or Q is true. So we have true, 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 then false. The next, the negation of that is false, 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 true. Then let's focus on the negation of P. So we have false, false, true, true. Negation of Q is false, true, false, true. Then for their conjunction, this can only be true if both of them are true. So there. Verifying that the biconditional are all tautology. As we can see, for biconditional, they should be equal values. So false, 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 true, false, 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 true, they are the same. So the biconditional are all true. And thus, their biconditional is a tautology. So you can use this as an equivalence relation. So we can interchange them as they are equivalent. And for some exercises, God bless and thank you.